We are ready to restart. So we're at this phase where both the client and the server have prepared the connection. Then at this stage, the client can do a send or a receive, by the way, and the server can also do a send or a receive with a small detail here that is quite peculiar of the way TCP works, is that when the accept is done, a new socket is created. So this server was using socket S1 to accept incoming calls. Once a call is accepted, a new socket is created, is forked if you want. This socket is listening to the same port, is connected to the same local port as the server. If it's a web server, then the local port is port 80. And it is on this socket that the actual data receiving or sending will be done. So now this server has two sockets, one at which it will be able to receive more connections. So in this case here, of this very simplified server, it will receive one block of data from the client, will do whatever needs to be done, close the socket, and after that will serve another client. Of course, if we have only such a simple server, it's hard to understand why we would fork the socket here, but most servers are more like this. A server handles a number of clients. If you're a web server, you serve not just one client, but a large number. So for every client that you're handling, you create a new socket, and each of these sockets can, in parallel or in pseudo-parallelism, can be used to serve one client each. So this server here has 1 plus 1, 2, 3, 4, 5, has 6 open sockets in parallel. Of course, those sockets will be killed when you do the close. After the close here, the socket is killed, and another one will be created when you do an accept. The reason is that typically you want to have some multi-threading on the server side. Sometimes people say that there are two kinds of socket here. There is a non-connected socket, and here there are connected sockets. So we can think of a connected socket as one that is associated with the IP address and port number of the remote end, of the other end, which is not the case here. Here, while you're waiting for somebody to send, anybody can send, so you are not specifically associated with anyone else. So this socket here is non-connected. And once you have done successfully done an accept call, then the socket here is connected to the other end. So one of the ping sockets can be used only to communicate with one specific other end, with one specific client. This is how the operating system views TCP sockets. It's very similar to UDP, with, of course, the fact that typically, if you are a UDP server, typically, if you don't use connected sockets, you have one socket for the server, whereas here, as we have seen, there will be as many sockets as there are active TCP connections on this server. Each of these sockets is associated with its own buffer. That's the reason why we need different sockets. We need a resequencing buffer, which is this buffer here, and one per TCP connection. The non-connected socket, the one that's used for connection request, has a buffer that is used only to store the SYN packets, and not this one here. Whenever a SYN packet is received, and then the operating system will create one of those sockets here. So there is a considerable overhead in TCP and a potential attack on the server. If you can generate a flood of SYN packets, then the server will be busy creating all those sockets, except if it uses a mitigation called SYN cookies to avoid that problem. With SYN cookies, what is done is when a SYN packet is received, the socket is not created immediately, but we do the SYN ACK. It's only when the ACK of the SYN ACK, so the third packet is received, that the socket is created. The reason being that if the SYN ACK is received, that means there was a TCP client really trying to connect to this server. It doesn't mean it's impossible to attack such a server, but it's much more difficult to attack such a server. To attack such of a server, you need to create a large number of TCP clients that are able to respond to the TCP SYN ACK. Whereas if you don't do that, all you need is to create a program that sends a large number of SYN packets and never responds to anything useful. So you can force SYN packets without creating SYN cookies, without creating TCP connections. We see also, like with UDP, that the IPv4 and IPv6 spaces are separate. So if you have a web server that works on IPv4 and that works on IPv6, then it needs to have two sockets, one for IPv4, one for IPv6. You can have higher layer interfaces, like the Python socket interface, that is able to hide the fact that there are two sockets by creating, for example, a layer that can accept both IPv4 and IPv6. But in principle, the operating system views the IPv4 and IPv6 stacks differently. Like it does if a server has multiple IP addresses, it will also have multiple stacks here. We have seen repeatedly that TCP views the data as a stream of bytes with no structure. If there is some structure, it has to be available at the application layer. For example, in the web, we use MIME headers and things of that kind to structure the data. But this is completely invisible to TCP. The TCP connection is typically identified by four things: source IP address, source port, destination IP address, destination port. This is a unique identifier of a TCP connections. The TCP PDUs, so the data that TCP uses, are called TCP segments. And the most important things to know about the segment is that it has a maximum size, which of course has to do with the fact that the IP packets have a maximum size. The maximum segment size is typically one of the options sent in the TCP header during when a SYN packet is sent. By default for IPv6, the minimum size is 1220. So that means any TCP implementation that works on IPv6 should support that packet size, and it's smaller for IPv4 because in the past there were IPv4 networks that had small packet size. We have seen repeatedly on the examples that TCP builds segments independent of how application makes it. You can have an application that writes 2 bytes, 5 bytes, 7 bytes, and TCP will send a packet of 12 a segment of 12 bytes. We have seen that fragmentation may occur sometimes at UDP. For example, UDP has a maximum message size of 64K. If the message is larger than the IP packet size, it will be fragmented. Multiple IP packets will be created. With TCP, this is forbidden. With TCP, if the application makes a write of 10,000 bytes, then TCP will create packets that are small enough to fit in the IP packet. The reason being that TCP will try to retransmit. Fragmentation is done at the IP layer. If a block of data is too large to fit in one packet and is fragmented by the IP layer, then, for example, 3 IP packets are created. At the destination, those 3 IP packets will be reassembled and delivered to the transport layer as one block. But if one of the 3 is missing, then reconstruction of the original block is impossible, so the entire block is lost. This is how it works with UDP. If we would apply the same thing with TCP, we would be confronted with a stupid design because we have a block of, say, 3,000 bytes. We split it at the IP layer into 3 IP packets. One of the packets is lost. Then IP is unable to reassemble it, declares that the 3,000 bytes are lost, whereas in reality only 1,000 was lost. Whereas if you do the fragmentation at the TCP layer, If you lose one block of 1,000, TCP will retransmit exactly that 1,000. If fragmentation is done at the IP layer, TCP will think that 3,000 bytes were lost and will retransmit the 3,000. That's the reason that we forbid fragmentation at the source for TCP. Quick question, what is a TCP server? I close in 5 seconds. Of course, the correct answer is A. That's the true definition of a server. I have some interference. We'll try to live with it. On the examples I gave, the server also does the receive, but there's no reason for that. The server is really the one that is ready for the connection to be opened. The logic of the application program will dictate what happens next. If it's a web server, you expect a web server to wait for a question from the web client, a GET or something like this. So a web server will start by doing a receive, but you can do other applications that would do different things. What we have seen is the basics of TCP. TCP is very complicated. It has a few tens of supplementary algorithms that are trying each to fix a number of little potential problems. I have mentioned one of them. That's the deadlock that might occur if I send a window advertisement that's equal to 0. So we need to manage it. So there is a small algorithm that says what you do when you have a window that's equal to 0. And this one says, once in a while, you can send a packet with a window of 1 byte. So that kind of things we will not see in detail. We will see one of them, which is when to retransmit a packet. Here is to give you a flavor of other algorithms that we have alluded to, when to send a packet. If an application is doing a lot of small writes, should you packetize or not? So there is an algorithm for that that's trying to avoid waiting too much, but also creating too small packets. And this algorithm is sensitive to whether you have the push bit or not when you send the block. There is a similar problem at the receiving end for when to send an ACK. If you receive a packet, should you send an ACK for every packet that is received? If you receive a flood of packets and the server is slow, perhaps you can wait until you receive 3 or 4 packets until you ACK everything in one shot. So there are local optimizations and also local algorithms that have been proposed, and there are many variants. Not all TCP flavors do the same. I've mentioned one deadlock due to the congestion window. There is another quasi-deadlock, which is called the silly window syndrome avoidance, which is what happens if a receiving application is very slow and reads the data byte by byte. That may seem stupid, but there are many cases where you're forced to do that. Because, for example, if there are markers in the data end of block of something, in order to know whether you have an end of block, one way is to read byte by byte until you see an end of block here. Of course, you can optimize that by reading chunks of bytes, but those things happen. Now, if you have such an application, assume the resequencing buffer is full, the application reads 1 byte. If you are very aggressive at the receiver, what will you do? You will send a new advertisement of the window saying there is a window of 1 byte. So the source will say, which was blocked, will say, now I'm unblocked, I will send 1 byte. This byte will be received. The buffer will be full again. When the buffer is, one byte is consumed, you will send it again. So you will have at the end a source and a destination that communicate by 1 byte packets. And both are very slow. So it's largely suboptimal. If they are so slow, you could wait until the application has consumed not just 1 byte, but perhaps a few hundred bytes, so that the source can send everything in 1 packet instead of 500 packets. So there is an algorithm for that, which is called silly window syndrome avoidance. I have mentioned that the SYN cookies that are meant to avoid the SYN flooding. essentially what the SYN cookies do is they allow the server to not create the socket that normally you create when you do an accept call, not create it immediately, but wait until you receive the third packet of the handshake, the ACK of the SYN ACK. Now, in the ACK packet, there is typically some information like the maximum segment size, and you also want to make the system robust by adding some cryptographic hash. Somehow you want that to make sure that the guy that's sending to you the SYN ACK is a response to the SYN that you have seen. Otherwise, of course, you would just push the problem. This is all done by putting all this information in the sequence number. So the sequence number that is sent by the server contains a cryptographic hash and the information of the MSS, the maximum segment size, that was sent by the source. All of that signed with a cryptographic hash. When the source responds, if it's a legitimate source, it will ACK this SYN ACK by sending the sequence number +1. So the server will receive this and will see whether it corresponds to what it expects. If it does not, it means it's a forged packet. I can delete it. If it does, it means it's a legitimate connection opening, and then I can create the socket. So that's an example of how the initial sequence number can be chosen to serve a certain purpose. And then what we will see is when to retransmit a packet. We have seen that retransmitting a packet is done when a timeout occurs. I send some data. I am a TCP transmitter. I associate with every packet a timer. And when the timer expires, I think the packet has been lost. This is one common way of doing reliability in any protocol. But we could do a bit better. For example, the problem with timers is that you never know what the correct value of a timer should be. What should the ideal value of a timer be? The RTT, the round-trip time. The round-trip time, including all the complicated parts of it, which are the time for the destination to respond. It might be sleeping, or this process might be sleeping because the destination is doing something else. And this time might be hard to predict. So it may be large for multi-programmed servers. So it can be several seconds. Now, since you don't know how large it can be, you have to find something that's larger than the worst case you're willing to handle. Because if you don't, if it's too short, you will retransmit and create unnecessary traffic. But if it's very large and there is really a loss, then you wait for a long time. So there is always a problem with timers. They have to be short if you want to be responsive, but they have to be large if you don't want to be wasting packets and resources. Another way would be to do this. Is this a good idea or not? I close in 5 seconds. This is an unusual quiz. I mean, it's not a quiz you will have at an exam because there's no real bad or good answer. I could say that that both A and B, are correct. If you think about it, if an application is sending, let's say, a large number of packets, and one of them is lost, then what is going to happen on the sender side, you will see, like we have seen 1 hour ago, that the ACK field, you will receive a lot of acknowledgements because only one packet is lost. But you will see that the acknowledgements indicate that somewhere the contiguous set that was received properly is not progressing. So the fact that you receive multiple acknowledgements is that are not let's say a duplicate ACK, is a hint that this packet is lost. Now, B is also right because it's not guaranteed that because I receive a duplicate acknowledgement that the packet is lost. It might be that there are multiple paths in the internet and one of the packets followed a different path and is late and will later be acknowledged. That is also a possibility, although rare. So what does TCP do? Well, it takes both and it uses what is called the fast retransmit heuristic in addition to the timeout that continues to exist, the one we have seen an hour ago. In order to speed up the detection of losses, if you see duplicate acknowledgements, then you declare that this packet is lost and you retransmit it. But you don't do it if you see just one duplicate acknowledgement, but if you see more than one, so how many is more than one? It's an operating system variable. I think Windows does 3, many systems do 2. Let's say if it is 3, that means whenever you will receive 3 duplicate ACKs, you will retransmit here. So here I'm showing 2 packets being sent. Packet 3 is lost. Then when I receive here the acknowledgement for packet 2, which is coming here, then when 3 more packets are being sent and successfully received, there will be ACKs that are duplicates. So the first one is not a duplicate ACK. Duplicate ACKs means the ACK field is the same as I have seen in a previous ACK. So here, this is a non-duplicate, but here I have 3 duplicates. If this heuristic is used, at this point, we will decide to retransmit the packet that is missing, and we know which one with the SAC blocks. It's 2000 to 3000. So we will retransmit P3, and then we will continue transmitting P7, if the window size occurs here. So this is how most TCP implementations retransmit packets today. Most losses are handled in this way, except perhaps the last. If you're transmitting a video file and the last packet of the file is lost, or one of the last packets, then there will not be enough duplicates, so you will have to wait for a timeout for retransmission. But for most applications that send a large number of packets, losses tend to be isolated and will be repaired in this way, which means in particular, the time until you repair it is auto-clocked, meaning if your connection is very fast, if the packets are streamed very fast, then the time to recover will also be very fast. If the connection is slow, this time will be slow. So you have an automatic adaptation which comes for free. Of course, when TCP continues to use timers, now there's an interesting interpretation that we will see again when we talk of congestion control. The timer is set conservatively, like any timer should be, which means it's very likely that you will detect a loss by something else than a timer. Now, if a loss is detected by a timer and you're not at the end of the connection, it probably means that there's been something really bad happening. There is a large number of losses, not an isolated one. If there's a large number of losses, if all the packets from 1 to 10 are lost, then there will be no duplicate ACKs because you've lost all the packets in the window, and then you don't retransmit anything. There's no duplicate ACKs. So this will be caught by timer expiration. But the interpretation, when a timer expires, is that something really bad has happened. The link is the connection, the channel between the source and the destination has become much worse, for example. And this is used by congestion control as a signal that we should dramatically reduce the rate at which we send. We'll talk about it later. And another side effect is that if one timer expires, then all timers are also reset, which means that if I'm sending packet 1 and the timer for packet 1 expires, of course, after that I had set packet 2, 3, 4, 5, 6, and there's a timer associated with all of those. Now, if packet 1 expires, the timer expires, it's very likely that very shortly after that, packet 2 timer will also expire. and 3 and 4 and 5 and 6. So in order to avoid all those unnecessary timer expirations, you reset all the timers for all the subsequent packets. When computing those timers, you need the estimate of the round-trip time. Now, the round-trip time, as we've seen, is very variable, primarily because of the destination server. So there is an algorithm in TCP to estimate the round-trip time. So whenever you start a TCP connection, you start also a timer round-trip estimation routine that does this code here. It is a computer science approximation of exponential weighted moving average. So it measures the round-trip time for every block of data that is sent. It tries to do that. I say tries because TCP does not have the concept of a block of data. TCP has just streams of bytes. But it tries to infer when a certain byte number is sent and I receive an acknowledgement for it, then I measure the time difference. So a TCP socket does all that stuff. Whenever it sends something, it remembers when it was sent. When the ACK comes for that, it measures the time first. There are heuristics to handle noise in that process. For example, if ACKs are piggybacked, if you send 2 ACKs in one packet, of course you count only the time for the second one, not for the first one, etc. So you get from this a measurement which is called RTT, and then you smooth it using this exponentially smoothing average, weighted average, alpha times the measurement plus 1 minus alpha, the previously smoothed value. So that's a classical formula for what is called a moving average filter. But you also estimate the standard deviation of the distribution of those times. It's not really the standard deviation, it is the what is called the non-standard deviation. It's not the square root of the mean of the square variance differences. It is the mean of the absolute difference. Why not the square? Well, we could argue why the square, but here the idea is all of this has to be implemented in the kernel for every TCP connection, for every packet sent. So you don't want to square things if you don't have to. So you take here an estimation of the average of this, which is the absolute value of the mean and which is the smooth value and the value that you have had here. So it's called an L1 error bound here, as opposed to the standard error bounds that are using squares usually. Of course, all those numbers are powers of 2, such that all those operations in C code, they are done by simply shifting bits, so they can be done very fast because you need to do them very often. Here's an example of what happens when we have some variability in the round-trip time. This variability will happen a lot because servers are largely unpredictable. This is the value that we measure, and say one value was very large, and the pink thing is the RTO, so the result of all this thing. The RTO, I forgot to mention, is the mean plus a number times the standard deviation. If this would be Gaussian stuff, we would say with 95% probability, we find a 95% coverage bound by taking the mean plus 196, for example, or 232 times the standard deviation. Here we take 4, and this is not really square stuff, so it's approximate, but it does the job. And you will see that the impact is whenever we see some variability, the round-trip time will jump and take a large value. Whether the variability is here positive and negative or simply positive. So those are the timers that TCP will compute. And you can see it can be seconds. This is why the fast retransmit is, of course, useful. In this animation here, in this cartoon, how was the loss detected? I close in 5 seconds. So we see a large variance in the answer. The correct answer is probably E, I think. Why? Because, well, we can never be sure about the timings because the timings are not shown here. So it might always be that the timer expires before anything else. So expiration of a retransmit timer set at 3 is always a possibility. So the only possible answers are D, E, F, G. Now, fast retransmit with TCP max dup ax equal 1. That means if I receive 2 times the same ACK, so if I receive 1 duplicate, that means 2 times the same, which would be this and this. So here I would have retransmitted here. Now, of course, you could argue perhaps this guy wanted to retransmit and could not, and this is correct. But probably, if it waited 3 times, it means this is probably what has happened. But admittedly, this could also be correct if the source on the left is very late. Voilà, this is most of what we will need to see about TCP. We'll come back to TCP in a module called congestion control, where we will see how TCP is used for performing congestion control. But this has nothing to do with all those timers and loss recovery. But before continuing, I'd like to conclude on a bit of theory and arguing why TCP is the way it is. A naive answer, and it's probably the correct one, it is the way it is because that's the way it was done. We could still ask the question, why, if it's not the optimal way, probably something else would have been developed today, which may or may not be true. We see that IPv6 is much better than IPv4, but is not fully deployed today. For that, we need to understand the issue of where to repair losses and errors in the internet. Right? So the first thing is to reason, so some reminder probably for many of you about capacity. The physical layer is not completely error-free, even though communication engineers try to make it very much so by adapting the rate and the modulation such that the bit error rate after all coding and modulation is very small, but that cannot entirely be guaranteed. And you know that there is on any channel, on the wires or other wireless channels, there is a well-defined capacity, at least if we can identify the physical parameters of the channel, which is, roughly speaking, the maximum rate at which we can transmit over this channel. Not quite, it's an upper bound on the rate, and with more and more work, we can approach this limit. It's called the Shannon or the Hartman-Shannon limit. So we could say the only thing that we need to do when transmitting, for example, with TCP or some more fancy TCP, would be to estimate this rate, then find the appropriate coding predicted by information theory, and code using this. But this is not what the internet does. The internet has decided a number of things. So the first thing is that because it's a computer network, that seems obvious today, but most of the internet today is not used for sending really data files. It's more for watching movie or listening to audio stuff, which is essentially analog things. So we could live with errors. But the way it was designed is no. The internet services must deliver sets of bits that are free of error with overwhelming probability. So if we detect an error, which we do we have seen a number of error detection code in the frame check sequence of the MAC layer, the UDP checksum, for example. If we detect an error, we simply discard the packet. Right? For example, if an Ethernet adapter receives an Ethernet frame that has some bit error, what will it do with the frame? It will simply drop it, right? Which is, now you could have imagined if you have a higher layer encoding mechanism that you're able to do something with a corrupted frame. If you have put some redundancy in the byte stream of the application layer, if you use some Reed-Solomon codes, for example, it's like reading from a disk and then there's a few bit errors, you can still recover a block from a disk. So you could do something like this. But the internet philosophy decided not to go in this, so we don't deliver packets that have errors. Now, Wi-Fi also does the similar frame check sequences, but does retransmissions. If from a Wi-Fi antenna to a device we detect that there is an error, or the packet is lost, or an acknowledgement is not coming, so in Wi-Fi there are acknowledgements, then the sender will try to retransmit it. Whereas with Ethernet, we don't do that. We've seen there's collision detection if we have old-style Ethernet, but this is independent of it. Here we're saying if we know the packet has been corrupted, in other words, if there is a packet loss, which is not the same as collision. Collision means we have not transmitted the packet. Here, if we have transmitted it successfully, we've resolved the collision, but there was errors or a loss somewhere, and the packet needs to be retransmitted. Wi-Fi will retransmit it. Of course, in Wi-Fi, there are zillions of options. There are almost 3,000 pages of standards for Wi-Fi, so you can decide whether you disable it, but by default, this is done. Whereas Ethernet does not do it. So why does one do it and the other not? Well, this calls to the philosophy of the internet, right? Here I'm showing two ways of repairing a packet loss. This is what we have seen is the TCP way. We are on a complex network where we've seen TCP from A to B, but in fact there's a network in between. I'll say something is lost. If it's lost here, then if it's the link AR1 is Wi-Fi, Wi-Fi will retransmit it such that the packet 3 will successfully be transmitted, and end-to-end there will be no loss. So TCP will not detect the loss. If this is Ethernet and the packet is lost, Ethernet will not bother and will not retransmit it, and it's TCP that will retransmit it. So we see we have two philosophies of retransmission. One is hop by hop, this one. Wherever we detect the loss from from one point to the next hop, if we detect it, we'll retransmit. We repair locally. Whereas here we repair globally. Why should we do this or that? Why does part of the internet do this and another part of the internet do that? What are the reasons? What should be done? Well, there are philosophical reasons. By philosophical, I mean design reasons. When you design an application, you have to take some philosophical decisions. You will do, if you're a good designer, you will say a number of principles. I will say, I will break the applications between A, B, C, and A does only this, and B does only that. And if you're smart and lucky, it will be exactly the correct decisions, and the application will be nice. The internet was done in this way, and one of the philosophies of the internet is the end-to-end philosophy. The internet says anything intelligent should be done end-to-end. The routers should be dumb things. They analyze the packet header, they look at the destination address, they go to their routing table, they decide where to send it, and they decrement the TTL. That's the only thing a router should do in principle. Therefore, if that's the only thing that routers should do, then they should not repair losses. I'm showing an animation where a block of 7 packets was transmitted and some packets were lost. There's a good reason for this design philosophy, which is that it's also what was special on this animation. Well, the packet did not follow all the same path. So because they don't follow all the same path, it will be very difficult for routers on R2, for example, to know that some of the packets are missing, for example. So they're not missing, in fact, they followed another path. So that's one of the reasons for the end-to-end philosophy, right? However, there's another reason for doing hop-by-hop recovery. It's information theory. If we compute the performance of a system that we model as an erasure channel. So we consider a path on the internet and assume the only thing that can happen is packets are successfully transmitted or are dropped. Then for such a system, it's almost trivial to compute the capacity of such a system. It's trivial and non-trivial at the same time. If P is the probability of losing a packet, the capacity of such a channel is R1 minus P. So if you lose 10% of the packet on a 10 megabit per second link, the capacity of this link is 9 megabit per second, which is a very optimistic result in some sense. It means there is a way of coding that will achieve a rate of as close to 9 megabit per second as we want. Right? And this way of coding is TCP, is retransmit the missing data. Okay, we will see how we go from this formula to a decisive conclusion on what should optimally be done in the internet next week. So tomorrow, the lab will start on using sockets, and we'll continue next week.